Hello, Algebra 2 Honor students. This is Unit 14, Day 2. Today, we are continuing talking about some radians. We're going to be evaluating trig functions with radians. And then by the end of the lesson, developing one of the most important concepts in Unit 14, which is what do the graphs of sine of x and cosine of x look like? Some really, really cool stuff today. So at the very top of the lesson here, you can see if you want to start taking your own notes, that I've listed what I think are some common radians that I want you to know the degree and radian equivalency for. These are ones that just come up a lot in our work because when I'm trying to evaluate and find the exact value for trig functions, we know that the special angles within our special triangles are 30, 45, and 60. So I really want you to, as you go throughout Unit 14, every time you see pi over 6, just know that that's 30. And every time you see pi over 4, just know that that's 45. The quadrantals that follow 90, 180, 270, 360, those are kind of important to know as well, and what their radian equivalents are. We know 180 is pi for sure, and then pretty much everything follows from there, right? Since 30 is 180 over 6, that makes sense that it's pi over 6. Since 60 is 180 divided by 3, that makes sense that this is pi over 3. So whether you need to commit those to memory or just get a little bit more practice to feel more comfortable with these equivalencies between radians and degrees, these are super important. And not only for this year, by the way, radians play a huge role in pre-calc and then into calculus as well. So once you get those copied down into your notes, let's go on to some evaluating practice. So for number 1, I'm going to evaluate something like sine of 5 pi over 4. And this is pretty much the same type of thing that we did in Unit 13, except this would have been degrees instead of radians. So we're going to sketch the angle first, figure out what quadrant we're in, figure out that reference angle within the triangle, label the sides, and then do the correct ratio using SOHCAHTOA. All right, so thinking about sketching this angle, that was what we practiced with a little bit on day 1 of this unit. So if we think about the fact that, 0 is on this side, if I go halfway around where pi is, that's 4 pi over 4. So I know that 5 pi over 4 is a little bit bigger. Full circle would be 8 pi over 4, right? 2 pi would be the same thing as 8 pi over 4, which means down here is 6 pi over 4, in between 4 and 8. Well, that tells me that I know exactly where 5 pi over 4 is. Okay. 5 pi over 4 is in quadrant 3. In fact, I know the reference angle is pi over 4. And that's the nice thing about using radians, is that the reference angle will always have the same denominator as the original angle that you're sketching. So if this reference is pi over 4, what we have to think about is, wait, what is that in degrees though, real quick, just so I know how to label the triangle? Oh, well, pi over 4 is 45 degrees. So now if I come back to my picture, I know that this is the 1, 1, radical 2 triangle. 1, 1, radical 2 is the pattern for those legs. Now, don't forget that when you're in quadrant 3, to get to this point, we went left and down. So the legs that have 1s on them, those need to be labeled as negatives. And that's pretty easy to forget, but I'll remind you how you can recall that once we go ahead and do the evaluating here. Sine is opposite over hypotenuse. So opposite the reference angle is -1, and the hypotenuse is radical 2. So in simplest radical form, if you multiply the top and bottom by radical 2 to rationalize here, you would get negative radical 2 over 2. Remember, to check whether this is positive or negative, you can do all-star trig class. We know that in quadrant 3 that tangent's the only one that's positive. So if you're dealing with sine of an angle in quadrant 3, the answer should in fact be negative. So you can do one of two things. Check it this way, make sure that you have the correct sign out front, and then also just double check that you've labeled the legs correctly, depending on what quadrant you're working in. Okay. So hopefully this process is looking familiar from Unit 13. Let's do a little bit more practice. If we did cosine of 11 pi over 6. Let's see what that would look like. So sketching an angle of 11 pi over 6. Here's 0. Halfway around is pi, which as a denominator of 6 is 6 pi over 6. So we know we're definitely past halfway. Full circle is 2 pi, which is 12 pi over 6. Sounds like 11 pi over 6 is just before I get to full circle, right? So in between 6 and 12 would be 9 pi over 6 down here. Now that we see where these border lines are, 11 pi over 6 is definitely an angle in quadrant 4. And like I said, the reference angle, how much more would I need to complete that circle? Another pi over 6 would get me to 12 pi over 6. So the reference angle is pretty easy to find, but what we now have to remember is what is this in degrees so that I can label the sides correctly. Well, pi over 6 is 30. So across from 30 is a 1. Across from 60 up here would be radical 3. And hypotenuse is 2. All right, to get to this point, do I need any negatives? Yep, I'm going down into quadrant 4, so the 1 should be the negative. Cosine's the ratio of adjacent over hypotenuse, so the adjacent is radical 3, and the hypotenuse is 2. So the final answer, radical 3 over 2. Makes sense that it's positive. All-Star Trig class tells me that in quadrant 4, cosine is in fact positive. So it makes sense there. If at any point during the lesson in this practice you feel like, you know what, I've got this, I can try these on my own. Before I do the example, why not hit pause and try it? All right. Tan of negative 5 pi over 3 is next. So to sketch this angle, just be careful that you're in the correct quadrant when we're sketching a negative angle. Okay. So we still start in the same spot, but negative we know means rotate around clockwise. So when I go halfway around at pi, I'm going to write this as negative 3 pi over 3. And then full circle is negative 6 pi over 3. So negative 5 pi over 3 is going to be just before I get to full circle. It's a little bit weird to label it this way, but I think it will help you. In between negative 3 and negative 6 is negative 4.5. I know it's weird to have that decimal as part of the fraction there. But that definitely tells me that negative 5 pi over 3 rotates around this way into quadrant 1. And if I've gone 5 pi over 3 in a clockwise direction, I need another pi over 3 to complete the circle. So reference angles should be pretty easy to come by when you're working with radians. Pi over 3 is 60. So across from the 60 is radical 3, 1, and 2. To get to this point, we're going right and up. So everything's positive in quadrant 1, which is good news. Tan is opposite over adjacent. So the opposite's the radical 3. Adjacent is 1. Well, radical 3 over 1 could just be written as radical 3. Okay. So it's, the examples really won't get much different than this. Certainly we could throw in some reciprocal functions. In fact, why don't we do one of the reciprocals, and then we're going to talk about how we can start developing some graphs for sine and cosine here. So for the last example that we'll do with evaluating for now is, why don't we do secant of 3 pi over 2. All right. Well, in order to do secant of 3 pi over 2, just like all the others, figure out what quadrant we're in. Here's 0, here's pi, which would be 2 pi over 2. Full circle would be 2 pi, which is 4 pi over 2. And in between 2 and 4 is 3. And oh yeah, 3 pi over 2 is one of those nice quadrantal angles. Maybe you knew that already before I went through this process. But 3 pi over 2 is right on the border, right there. So we know that whenever we're on the borderline, we have to use the unit circle. So that's going to be 0, negative 1, the coordinate point. Secant's the reciprocal of cos, and cosine goes with x. So if cosine is x, secant is going to be 1 over x. The x value at 3 pi over 2 is 0, and 1 divided by 0 is undefined. So much later on in this unit, we're on day 2 right now. By day 7, we're going to graph secant. And when we graph secant, something weird is going to happen at 3 pi over 2. Because we know that secant is undefined. Maybe you already kind of know what that is, but some foreshadowing of what's to come. Okay. And speaking of the unit circle, let's create a completely filled in unit circle, because the unit circle is pretty critical for us to be able to understand what the graphs of sine and cosine look like. So quick unit circle here. Okay, if we label those 4 points, 1, 0, 0, 1, negative 1, 0, 0, negative 1. We know this is 0 pi and 2 pi for full circle. Up here is pi over 2, pi, and 3 pi over 2. So label all those angles in radians. And what I want to be able to do is make a list, sort of a table of values based on the unit circle. I'm going to give you some radian angles. So theta in radians. And what I want you to tell me in the right column is what would sine of theta be? Okay, so when I plug in an angle for theta, what's the output when I take sine of theta? And we'll start at 0. And then we'll do pi over 6, pi over 4, pi over 3, pi over 2, pi. 3 pi over 2, and then 2 pi. So kind of a lengthy list here. And if you're looking at some of those radians that I've given you in the table here, you're like, wait, those aren't on the unit circle. And to be honest, you actually could use the unit circle to do what's happening at something like pi over 6. But we'll use our special triangles to do some of these, okay? So when we start at 0, sine of 0, remember, if we're just doing sine, we're looking at only the y values, okay? So we're looking at the y values on the points on the unit circle. The y value is 0 to start. So when I go to make my graph for sine theta, it definitely goes through the origin at 0, 0. In fact, I'm going to kind of jump all the way down to pi over 2 right now because that's the next easiest thing for me to evaluate based on the unit circle. Sine of pi over 2 is 1. Sine of pi is 0, just looking at the y values here. Sine of 3 pi over 2 is -1. And then sine of 2 pi is 0. These are all coordinate points that we're going to plot when we make our graph in just a moment. By the way, the graph that we're going to complete is on page 15 of the packet. So if you want to start finding that, we're going to do that in a few moments. All right, so how do I do the rest of these? For pi over 6, pi over 4, and pi over 3, it's up to you if you want to make some quick reference triangles. Pi over 6 is 30, so this is 1 radical 3, 2. Pi over 4 is 45, so there's my triangle there. And by the way, if this angle is pi over 6, this is the pi over 3 up here. Sine of pi over 6 is 1/2, which of course is 0.5. Sine of pi over 4 we know is 1 over radical 2, which is radical 2 over 2 rationalized. But what I'm actually more concerned with is what's the decimal there? So 1 divided by radical 2 is approximately 0.707. And although we would never list that when we said what's sine of pi over 4, we would just say 1 over radical 2. The only reason I'm getting that decimal for you is so you can kind of get an idea as to what the graph's going to look like when I plot the point there. All right, and then finally pi over 3, that last one, oops, not pi over 3, but sine of pi over 3 is opposite over hypotenuse. That's radical 3 over 2. And I believe that's going to be about 0.866. We'll double check it. And that is 0.866. Okay. So all I want you to see is that if you were to go from 0 to 1 for y values, when the angles go from 0 to pi over 2, what's happening in between? It's going to be like a straight line that connects them. Or what would happen, at pi over 6, we're at 1/2. At pi over 4, we're at 0.707. We're going to see how this kind of helps us to generate the graph of what the sine curve looks like. All right. So if you found page 15 in the packet, it looks like this, graphing sine, cosine, and tangent. We're not going to do tangent today. We'll just focus on sine and cosine. All right. But if we take a look at the example of graphing the sine curve, here's how I want you to label your axes. So if you notice based on the table that we made, the highest y value we ever got was 1. And the lowest y value we ever got was -1. And that happens to be the range for sine of x. So for the graph of y equals sine x, the range of outputs has to be somewhere from -1 to 1. We know we're starting at 0, 0. But then as far as the labels that we're going to put on the x-axis here, we have to decide on kind of a certain scale. And what I'm going to do is I'm going to make every 3 spaces another pi over 2. So if that's pi over 2, then if I go another 3 spaces, this would be pi. Essentially, every 3 spaces, you're going to label the quadrantals. So we've got pi over 2, pi, 3 pi over 2, and 2 pi. It makes sense to label the x-axis that way because that's what we had in kind of our x list in the table here, from 0 to 2 pi. All right, so what happens is that pi over 2, if you look back at your table, we're at a height of 1. By pi, we're back to 0. 3 pi over 2, you're going to come down here to -1. And then 2 pi, you're back at 0. So the only other reason I added in a couple of additional angles, like pi over 6 and pi over 4 and pi over 3, is just to give you an idea as to what is this going to look like. Is it going to be like a straight line connection, or is it going to be more of a curve? Well, pi over 6, I'll tell you, is actually right here, right? Because 30 would be, if this is 90, 30, 60, 90. And at pi over 6, the output there is a half. Okay, and by the time I get to pi over 3, which is 60, the output there is like 0.866. So what's going to happen is it is going to curve through those points and then curve down and come down to pi. And then it will curve down towards -1 and then back up by the time we get to 2 pi. Now, the cool thing about this graph is that it doesn't necessarily stop there. That's the last angle that we've plugged in. But if we kept going and we plugged in more angles beyond 2 pi, we're going to see this same exact pattern repeat again, because as I go around the unit circle over and over and over again, you're going to get those same values to repeat themselves. So it's going to eventually come back up again and then go back down again. It's going to follow that pattern forever and ever and ever. So the domain of the sine function, just so we can list it quickly, the domain is all real numbers. But notice how the range of outputs is only from -1 to 1. Oh, and by the way, I didn't graph any negative values, but we could actually continue that same pattern in this direction as well. All right, really quickly, while we're at it, let's go ahead and take a look at what cosine of x would look like. Now, how am I going to get cosine of x? Cosine of x, I'm going to label the axes in the same exact way. Here's 1, go down 3, there's -1, and let's do every 3 spaces is pi over 2. We can generate the cosine curve just as easily as the sine curve by using the unit circle, but this time we're going to look at the x values, right? Because cosine is x. So cosine of 0 is 1. So your very first point you should plot is at 0, 1 up here. Pi over 2, cos of pi over 2 is 0. Plot that. Cosine of pi is -1. Go ahead, plot that. Cosine 3 pi over 2 is 0. And then 2 pi is back to where I started, which is up here at 1. So you can see the cosine curve is going to look quite different, and it is a curve. It kind of looks like one big valley here. And it also would continue that same pattern forever and ever and ever. Okay? And it would go to the left and continue that same pattern as well. So that's exactly what the cosine curve looks like. Unit circle is really great in helping us understand that. Tangent's a little bit of a different ballgame, so maybe we'll wait on tangent until we're in class together. But there's so much more to come with trig graphing, especially with transformations of sine and cos. So we'll see that in the next few lessons. That's it for today. Have a great rest of your day.